So section 1.2 of this text is an introduction to logic and to quantifiers. We're primarily going to focus on logic. We did cover logic in finite math in chapter 11, and we had an Alice in Wonderland project. So I feel like you guys are going to be pretty comfortable with logic. I did go ahead and post some stuff from last semester's files, just so you guys have more videos of truth table examples. So friendly reminder that a proposition is a statement that's either true or false, but not both. So some examples of propositions are Abraham Lincoln was the 16th president of the United States, which I should have capitalized, but that is true, right? The Blues won the Super Bowl, that's false, because the Blues play hockey, not football. It's also important to note that we may not have enough information to know a statement's truth value. But as long as it still has a truth value, even if we don't know what it is still a proposition. Some examples that are not propositions would be, he's a really nice guy. Get your feet off the table. Is today Wednesday? Those don't have a truth value. So today is not Wednesday, that's false. But the reason this isn't a proposition is it has a question mark, so no questions can be propositions. So let's go through a few. First thing I want you to know that a proposition's truth value is either true or false. I'm going to write that with a capital T for true and F for false. And for those of you interested in going into computer science, it might be good for you to know that in computer science, sometimes a true value is represented with a 1 and a false value is represented with a 0. Little fun fact for you. So let's see if the following statements are propositions, and if they are propositions, I want you to state their truth value. So A is the number 13 is a prime number. Well, we know that to be true, and it's also a proposition. Doorbell broken, please knock. Okay, that is not a proposition. C is the number 18 is evenly divisible by 5, right? Well, 18 is not evenly divisible by 5. I'd be left over with 3/5. That's not a nice number. So this has a false truth value. The integer 2n is even, where n can take on any integer value. That's going to be true, right? Any even number is divisible by 2, so 2 times -1 would give me -2, 2 times 1 would give me 2, 2 times 7 would give me 14, and that would always be even. So this has a true value. The integer n is even. Well, that's true half the time, right? That's true when n is 2 or 4 or 6 or 8, but it's not true the other half of the time. So this is going to be false because it's not always true. Next, the number of grains of sand on Earth is larger than the number of stars in the sky. So this is a proposition, I want you to know. But do we know whether this has a true or a false truth value? No. Its truth value is unknown, and that's okay. Compound propositions are formed by combining two propositions or statements. In order to develop our rules for logic, we need to be able to work with our logical statements, not just specific examples. So we're going to denote our propositions using variables like P, Q, and R. So you might remember our truth tables from finite math. So the conjunction of two propositions P and Q is the statement P and Q, and we write this P dot Q or P upside down VQ. In the last text we used this notation, now we're going to use this notation. If you want to keep the old notation, that's fine. You just really need to know what this means. And this is and. So it's only true if both P and Q are true. So when P is true and Q is true, P and Q is true. If one of them is false, then P and Q is false. And if both of them are false, then P and Q is false. A disjunction is what we call our OR statement, right? So the disjunction of two statements P or Q is written P or Q or P plus Q. There's two different ways to note it. We're going to use this notation here. So what this means is this is the inclusive OR. So only one statement needs to be true, or both can be true in order for the statement's truth value to be true. So if I have true or true, I get true. True or false is true. False or true is true. And false or false is both false. This is only false if both P and Q are false. Negation of a proposition is the statement not P, and then it takes on the opposite truth value. So this can be written tilde P, P bar, whatever this little symbol is, but in our notation we're going to use this tilde P. This means not P, negate P. So if P was true, it becomes false, and if P was false, it then becomes true. The conditional of two propositions P and Q is the statement P implies Q. We write this with an arrow. So true implies true is true. True implies false is false. False implies true is true. And false implies false is also true. The exclusive OR is the statement that P or Q, but not both P and Q. We proved it how it's equivalent to this statement in our last course. So this is only true when P or Q are true, but not both are true or both are false. So I only can have one of them. Okay? Inclusive OR, what we talked about before, is kind of like you can have cookies or ice cream for dessert, but you could pick cookies and ice cream. In this option, you only get to pick one. They're only cookies or ice cream. You can't have an ice cream cookie. Okay. Biconditional is when two propositions are logically equivalent. Last class we denoted it with this two-way arrow. Now we're going to use this like triple equal sign. So P is logically equivalent to Q, means they both have the same truth value. Whether that truth value be true or truth value be false. So P and Q both true, that means they're logically equivalent. True and false gives us false. False and true gives us false. But if they're both false, that's true that they are logically equivalent. The contrapositive of a proposition P implies Q is the statement not P implies not Q. So one way to think about that is the statement that if it rains, then they cancel school. The contrapositive statement of this is if they do not cancel school, then it does not rain. It rains is my P, they cancel school is my Q. The converse of a statement P implies Q is the statement Q implies P. So look at the statement, if I hit a target, that can be our P, then a bell will ring. The converse of this would be if a bell does not ring, then I did not hit the target. If a bell does ring, then I did hit the target. It shouldn't have these two knots in here in order to be the converse. If I have the knots in there, then it's the contrapositive. So friendly reminder that logic has its own kind of PEMDAS. We call this order of precedence. And order of precedence says that we go by and solve the truth value of logical statements starting with parentheses, but without parentheses, we use the order of precedence, which is not, and, or, implication, or biconditional. Remember, and now we're using a dot. Okay? So last semester I had you guys come up with, I got a couple of mnemonics to help us remember No app, but I'd love some more. So a truth table is a table that includes a column for each simple statement, a column for the compound statement, a row for each possible combination of truth values for our simple statements, and the column for the statement form has its truth values depending on the previous truth values in the corresponding row. So let's go through an example of making a truth table. I did go ahead and post the videos from last semester that go through some more complicated examples of truth tables. Keep in mind that they will have last year's notation, and is the only one that really changed. So let's go ahead and write a truth value for P or Q implies P. So I need a column for P, I need a column for Q. True, true, false, false, true, false, true, false. This is so I can every possible combination. First thing I'm going to look at is in parentheses here, I've got Q implies P. This is only false if true implies false, so let's take a look. Here I have true implies true, which is true. Here I have false implies true, which is, I still want that to look like a T though, which is true. I have true implies false, which is false, and false implies false, which is true. Now I want P or Q implies P. So I have to look at my values in my P column and my Q implies P column. Remember, or is true as long as one or the other is true, or both of them are true. So if I have true and true, that's true. True and true, that's also true. False and false, that's false. Right? Because we're looking at or. And then false and true, that's also true. The last thing I want us to do is determine the truth value for each of the statements below, given that P is true, Q is false, R is true, and S is true. So for problem number 1 here, I have P or Q implies R. So P is true, Q is false, implies R, which is true. So I'm going to simplify this using parentheses and order of precedence. So true or false, remember or means one or the other has to be true, so that's true. So I get true implies true, which is true. So the number 1 has a truth value of true. For 2, I have P and Q implies S, or R implies S. So I have P, which is true, and Q, which is false, implies S, which is true. See, I'm just substituting in the truth values for our variables. Or R implies S. Well, that's true implies true. So we need to simplify this. First thing I'm going to do is this implication in parentheses. False implies true. That is true. Or true implies true. That's also true. True and true inside these brackets here is going to give me a true. So I have true or true, which would be true. So 2 also has a truth value. Let's go ahead and make ourselves a little more room for numbers 3 and 4. For 3, I have not P and Q implies R and S. So I'm going to go ahead and substitute in P is true, Q is false, implies R is true, and S is true. So true and false, that's going to give me a false. but I have not false, which becomes a true. And this implies true and true, which is true. So now I have true implies true, which is also true. Notice how for number 4, it looks really similar to number 3, except I added an extra set of black brackets. Let's see how that alters our truth value. Changing back to blue. For number 4, I have not, true and false implies true and true. That gives me not, true and false becomes false, true and true becomes true. I have false implies true, which is true, so not true gives me a false. Finally, we got a false truth value. So here's the section 1.2 homework. It's only problems 1, 2, 5, 6, 7, and 8. It's not a really long homework. It's going to have you make a couple truth tables and prove some, show some truth values just like we, for statements, just like we did in the past, in the previous 4 examples.